All right, so last chapter we are going to look at is part of chapter 11. Okay, we'll do through section 11.3. We won't get to anything after that. Some of the topics that come after that is a little bit of statistics and probability, which isn't strictly a pre-calculus topic anyway, but they put it in there. But we're just not going to get to it. Okay, so what we are going to get to is sequences and series. So basically, the goal is going to be to figure out patterns, right, for predicting terms in a sequence. Especially if we want to predict terms that are, like, let's say you had a sequence thousands and thousands of numbers long, and I give you the first few. Well, if you want to find a term in that sequence that's way, 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 way down, we don't want to have to, like, figure out every single term up to the one that we need. We want can we come up with a formula that I can just plug in? Let's say I want to know the 3,432nd term. I just plug in the number 3,432 into a formula, and it tells me what would be that term automatically. So that's a big part of what we're going to do. So basically, a sequence of numbers has a specific order to it, and it's generated from a formula. Our book designates sequences with lowercase letters. So this particular sequence is called sequence B. And the position in the sequence, the first one is called position 1. The second number is position 2. Third number, position 3, and so on. The way that you can denote that in a shorthand is you use the letter for your sequence and then a subscript with the number. So B sub 3 is the third term in sequence B. B sub 70 is the 70th term in sequence B. And B sub n is some term, an unknown distance away, that is marking the end of this sequence. We know that this sequence has an end to it because it doesn't have ... at the very end. If you end a sequence with ... that means that it keeps going. If you end a sequence with B sub n, it means that there is some term somewhere that marks the end. It could be 100 terms away, it could be 200 billion terms away, we don't know. But there's an end to this sequence somewhere. Okay. So in order for a sequence to be unique from another sequence, there has to be some rule or formula for calculating terms. If it's impossible to find a rule for calculating the terms, then you don't have a sequence. Okay. And when I say impossible, I mean not that you can't figure it out, but there is one. I mean, like, there is no formula to predict the terms that are coming up. They're like random. That's not the kind of sequence we're talking about. We're talking about sequences that are not random. Okay, they are defined by a formula. All right, so let's look at this one. This particular sequence is an infinite sequence. Okay, I've listed the first 4 terms. Then I put ... and then I listed some arbitrary term much later. Could be 100 or 200 terms later. But then there's even more terms after it. This particular sequence I've named A. And what I want to do is come up with a formula to predict the nth term in sequence A. So does anybody think they see a pattern or some type of formula that we could use to predict the nth term in sequence A? Yep.
I can see that's adding 3 every time, like it goes up.
Can you be more specific about what you're adding 3 to?
You're adding 3 to 2, and then just keep adding 3 to whatever number was the last.
Yeah, you're adding 3 to the number that came before the one that you're looking for. So if this is the term that you're looking for, how do you think you would represent the one before that? Yeah? Yeah?
A7 minus 3.
A sub what?
N minus
n minus 3, that would be 3 more than the one we're looking for. 3 further back. Yep.
A sub n minus 1.
Right, a sub n minus 1. That represents the one before the one you're looking for. And what did we say we do to that one? Yep.
Yeah, 3.
Yeah, 3. So let's say you wanted to know the 900th term in that sequence. Based on the formula, how would you write the 900th term using the formula up above? Yeah?
A sub 899 plus 3.
So it's the 899th term plus 3. Do we know the 899th term?
No.
No. Okay, so then we need to find that one. Okay, based on our rule up above, how do you find the 899th term?
A sub 898 plus 3.
A sub 898 plus 3. All right. Do we know the 898th term? No. This is going to take a while. All right. So this formula is correct. It's called a recursive formula. The problem is it's easy to see, but it's not very useful. Because to figure out a specific term in a recursive formula, you have to know every single term up to the one you're trying to find. We don't want to have to do that. So let's see if we can find a different formula. So instead of looking at the pattern as adding 3 each time, I want you to think about something you could do to the position number. Okay, this is position 1, 2, 3, and 4. Is there something you could do to the position number to turn it into the term number? Like something you can do to 2 to make it 5. Something you could do to 3 to make it an 8. It has to be the same thing each time. Anybody see the pattern looking at it that way? Yeah? Times 2 and minus 1. So if you do 3 times 2, what do you get?
6.
And then if you minus 1?
You get 5.
Yeah.
But if you add that,
What's that?
if you add that to the term,
So it's got to be something that you can do just with the term number directly, kind of like what you said, but that's not the formula that works here. But it's that idea. You're pretty much you're on the right track. Yeah.
3a minus 1.
Yeah. Times by 3 and then minus 1. If you take the position number and times it by 3, so let's try that. 4 times 3 is 12. 12 minus 1 is 11. 3 times 3 is 9. Minus 1 is 8. So now, to find the 900th term, it's very easy. Triple 900 and then minus 1 from it. So it's 900 tripled is 2,700 minus 1, 2,699. That would be the 900th term in that pattern. Okay. So this is called an explicit formula. An explicit formula is a little bit harder to come up with, but it's way easier to use. A recursive formula is easier to come up with, but it's not that useful. So most of the time, we're going to try to figure out explicit formulas if we can. Yes?
How do you get the beginning number of the sequence to?
That has to be given to you.
No, from the left. Like, how would you? Because the thing is, how would that prove? Is there a way to prove like the formula with that? Because if you see, because like the first term as a 1 minus 1, so a is 0 plus 3, and that would say that means a, so then equals 3.
So you're going to be given the first 2 all the time. You have to. If you're not given the first 2, or you got to be given some amount where you can't come up with a formula.
Solely based. So you don't need to have it proven for the first 2 terms?
No, the first couple terms are usually just given to you. Yeah.
but your formula you make doesn't need to work with them.
No, it just has to work for all the ones that come after it. But I mean, this formula does work for all of them. The problem is if you try to do it on the first term, you would end up with the first term is the 0th term plus 3. And there's no such thing as the 0th term.
And then
So
second term.
it does work for that one. Yeah. It's the
Good.
first term plus 3.
Oh,
Yep.
So if you're given just an equation, it's asking for the first term, would you start at 0 or start at 1?
You would start with 1.
Okay.
Yeah, the first term. So like if I just gave you this formula and I said, tell me the first term, you would plug in the number 1. The number you plug in is the position you want to know. Yep. All right, so what I want to kind of do is make a connection between like a function and then a formula that predicts terms in a sequence. We just found this formula. Where was it? A sub n equals 3n minus 1. You could kind of think of that as like f of x equals 3x minus 1. Now, when we're graphing this, forget about sequences and just pretend like you're graphing this on a calculator. What's the domain for f of x equals 3x minus 1? Yeah?
all real numbers.
Yeah, the domain is all real numbers. Now I want to think about this formula in the context of just a sequence. This represents the term that you're looking for. When you think about it that way, what's the domain for x? If x has to represent a position in a sequence. Yeah?
It can't be 0 or anything below 0. It needs to be greater than or equal to 1, but it has to be integers.
Right. So when we're thinking about this formula, which is the kind of formula we're going to come up with, you've got to start thinking in your head the domain is just numbers that are integers from 1 and up. It doesn't make any sense to plug 1.4 in for x here. Not when you're thinking about a sequence, because there's no such thing as a 1.4th position. You have the first position, second position. There's nothing in between the two. So that means if you were to graph something like this, if the domain is all real numbers, it would look like a line. How would the domain look when you graph it if you're only plugging in integers for x? How would your graph look instead of being a line?
Second.
Yeah?
The steps,
It would just be dots. Exactly. So your sequence would look like this when you graph it. It would just be dots. There would be no connection between the dots because there's no term in between two terms. Like second term, third term, nothing in between. Right, so that's basically the idea that I'm getting at right there. So all the formulas that we come up with today are going to have a domain of positive integers. All right, so there are two types of sequences. There are sequences that have an end and sequences that don't. If a sequence is infinite, infinite means that it goes on forever. That means if you had a formula to predict the terms in the sequence, just make up something. That means that x can be any positive integer. Any positive integer. Because there is no limit. The sequence goes on forever. If you have a sequence that is finite, then the numbers that you plug into your formula cannot be anything. They stop somewhere. If you had a sequence, let's say you had a sequence with 10 terms in it, that means n could be 1 through 10. N could not be 11, because there is no 11th term, it stops at 10. So a finite sequence, basically the formula for it would have a domain that is a subset of all the integers. Specifically, every integer from 1 up to n, where n represents the last term in the sequence, last position. And you've got to kind of differentiate the idea of like a huge sequence versus an infinite sequence. If a sequence has 200 billion terms, that's a lot of terms, but it's not infinite. It's finite. It stops at 200 billion, and it doesn't keep going. Right? Yep.
It's kind of unrelated, but kind of related, because you're talking about like just 1, 2, and nothing in between. There's countable infinity and uncountable infinity. So like countable infinity is just like 1, 2, 3, 4, 5, like so on and so forth. So you pass out, but then uncountable infinity is like 0.000001. Every time you think you know what the start is, you can almost go smaller, so you can't really count it. So like it's almost impossible to like actually show stuff for that, because that's uncountable infinity, because there's like an infinite number of like units between 1 and 2, instead of like the countable infinity, which is 1, 2, 3, 4, 5. So
Yeah.
like,
So that's an important topic, not something we're really going to get into with this, but yeah.
But like for the finite sequence, that's like the kind of like the countable thing, where like it's the a sub n, right? And the finite sequence, is that the a sub n one?
So yeah, finite sequence, it stops. So there might be 600 terms in the sequence, and you're done.
But the infinite sequence just has the dot dot dot.
It just keeps going. Yep.
Okay.
So here's a formula, and what I want you to basically do is just tell me, using this formula, what are the first 3 terms and the 15th term. So the notation for that is on the board, A1, A2, A3, and then A15. There's no reason why I picked those, I just picked some terms to find. All right, so when we want to find the first term, what number do you plug in for n? 1. So if you plug 1 in for n, what do you get for the first term in this sequence? 0. Yep. 0. All right. What do you get? Let's leave it as a fraction. What do you get for the second term? What is it?
So 1.5.
And as a fraction, it would be
3 halves.
3 halves. All right. How about for the third term? 8 thirds. And how about the 15th term?
224 over 15.
224 over 15. Now, if you look at that one's probably far enough down that you can see what this sequence is approaching. If I ever ask you what the limit of a sequence is, I'm asking you, does it look like it's getting close to something? So let's see. Let's take 224 and divide by 15 and see what that is. In fact, we could do all of them. The first ones don't tell you as much. So this one is 0. This one's 1.5. 8 thirds, that's, what's that? 2 2/3. So it's about 2.67. And this one is going to be about 14 point something.
933 repeating.
14.93 repeating. Does anybody see a connection between the number that you get when you divide these and something else here? This is getting very close to something. Yeah?
It gets really close to the denominator, but doesn't reach it.
And essentially, what is the denominator there?
15. Well, if you're talking about E15.
How about in general?
And
The denominator represents, yeah?
And
Which is the?
Number in the sequence.
The position in the sequence, yeah. So what's essentially happening here is as you go further and further down your sequence, the value of the term is approaching its position number. It'll never quite reach it because of that. You're always throwing the numerator off by 1. which starts to become less and less and less significant as n gets really, 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 really big. Like if n is 1,000,000, there's not much difference between 1,000,000 squared and 1,000,000 squared minus 1. It's a very, very small difference. Okay? But for small numbers, that minus 1 has a bigger impact. Okay? So the position here, this number is approaching the position value, but never quite reaching it. It's always a little less. Okay. All right, let's try this one. What happens when you raise -1 to a power? Yep.
If the power is even, it should be positive. If it's odd, then it will be negative.
Right, so essentially what -1 to the n does is it causes an oscillation in the sequence. Positive, negative, every other number. That's what a -1 to a power will do. So if you plug in 1 for n, what are you going to get for your first term?
-2.
You're going to get -2.
Oh,
What if you plug in 2?
4.
You get 4. And if you plug in 3?
-6.
negative 8.
-8. What if you plugged in 4?
10.
No.
16.
16, 5. I think you're still calculating in your head versus seeing the pattern that's happening. So -2, +4, -8, +16,
-32.
-32,
768.
+64, -128, +256, -512. So it's doubling each time, and you're just changing the sign. Okay. So now with 15, well, we know if it's going to be positive or negative. Which one is it?
Negative.
Yeah, it's a negative. And then 2 to the 15th power.
32,768.
Yeah, so 32,768. So if you want a sequence to oscillate between positive and negative, that's one way to do it. If you try to graph something like that on the calculator, you really can't. The calculator can't handle something oscillating, but it would basically look like this. Each time, you're doubling like how far away you were and oscillating above and below the x-axis. All right, so we've kind of already talked about that concept. A sequence is basically, it's a function, meaning if you plug in a number into a formula, as long as you do it correctly, we're all going to get the same answer. There's no way you can get more than one answer. There is only one number in the third spot in the sequence. That means it's a function. You can't get two possible numbers in that spot. There's only one. But remember, we're only dealing with a function that has a domain of positive integers. It doesn't make sense to plug in negative numbers because you don't have negative terms in a sequence. Like, I mean, you don't have negative, like the negative third term. There's no such thing. And there's no decimal terms or decimal positions. Yeah.
Which thing does that look most like? Sine, cosine, or tangent for like the oscillation thing?
What's that? It's,
Which graph does it look most like? The sine, cosine, or tangent for the oscillating graph?
well, none of them. Because it, as you keep heading down, it's like it's oscillating. It starts to like just keep spreading out forever.
So it doesn't look like any.
No,
Okay.
no. It's unbounded. It just keeps doubling each time and going above and below the x-axis. Well, we kind of already did this. This is the problem we just did. When we plugged in the first term here, I think we got 0. So first term was 0. What was the second term?
1.5.
Yeah, 3 over 2, so that was 1.5. And the third term,
8/3.
yeah, 8/3, so that was
2.67.
2.67. And then we did the, I can't all go all the way to the 15th term, I don't have enough space, but I could do the 10th term. That would be 99 divided by 10, which would be 9.9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9.9. So what you can see is as you keep going down, this red dot is going to get closer and closer and closer to the line that's above it. But it's never quite going to be on that line, no matter how far you go. All right. Any questions on that? And remember, don't connect the dots. Okay, there's no connection. Okay, so the formulas, I mentioned 2 types, explicit and recursive. All the formulas I've given you so far, that one, that's the same one, the one that we had down below, they all allow you to find any term you want in the sequence directly. You want to find the 7,000th term? Just plug in 7,000. You don't have to find the 6,999, 6,009. You don't have to go backwards through all of them. Okay. That kind of formula is called explicit. Okay. The other kind of formula we can have is recursive. Recursive is usually, again, easier to figure out, but it's not that useful. And there is a process to turn a recursive formula into an explicit formula. Sometimes it's pretty easy. Sometimes that can be extremely hard to convert a recursive formula into an explicit one. Okay, I'll show you a recursive formula that I think you've all seen before, but it's challenging to convert it to an explicit formula. So the way that a recursive formula works is I have to start you off with the first few terms. How many is a few? Probably 3 or 4. Okay, so I'll start you off with some terms. If I don't start you off with enough terms, then there may be more than one way to figure out a formula. So like if I did something like this. Bless you.
Thank you.
What's one potential pattern that you might see there?
+4.
Could be +4 each time.
Times 3.
It could be times 3 each time. I was thinking of cubing it and minusing 2. 2 cubed is 8, minus 2 is 6. No, I wasn't really thinking of that. It's just a pattern that fits. So you don't know what the pattern is. That's why I'm generally going to give you at least 3 or 4 terms. All right, so the first few terms are going to be given. And then each term is defined as doing something to the one that came before. Okay, that's a recursive formula. So any question on the difference between explicit and recursive? Okay. So here's an example of a recursive formula. I'm giving you the first term. I'm telling you what to do to get the next term. And now I want you to tell me the next term. If you had to summarize that for somebody that doesn't really understand what recursive notation is, how would you explain in words what this formula is telling you to do? Yeah.
The number in the sequence you're looking for is the number before plus 3.
Right, it's the previous 1 plus 3. So, based on that, what would the second term in this sequence be? 5. And the third one? 8. And the 2000th one? Well, you're not going to be able to figure that out quickly because you have a recursive formula. All right. And if you're coming up with like some trick, like, oh, it's just take the position you want to know, triple it, and -1, well, then you're not really using a recursive formula anymore. You've just converted into explicit. But that is the pattern. If you triple your term position in -1, you'll get the number in that position. For simple patterns, what would I consider simple? Adding a number each time or multiplying by a number each time. I can show you ways to figure out those patterns very easy all the time. If the pattern was something like you take your number, you square it, you triple it, then you subtract 4 times your number, that's a complicated pattern. There's no way I can teach you an easy method for figuring that out. And most of the time, we're not going to have one that complicated. Okay, determine the first 4 terms and the 8th term. Okay, what's the first term there? How do you figure that out? It's given. So you can't do a recursive unless they give you the first one. What's the second term going to be? 6, third term. 10, and 4th term. 14. Now that's all they asked for the beginning. They want to know the 8th term, but this is a recursive formula, so we don't have a quick way to jump right to the 8th term. So we just got to kind of figure them all out. So what's the 5th one? 18.
22.
22.
26.
26.
30.
There we go. Okay, again, if they asked me for like the 9,000th term, that's not the way I would have done it. But I only had to go through 3 before I got the one I wanted. So that wasn't too much work. Any question on that? Yes.
Is there a way to only use a recursive formula to find the explicit formula, not looking at the terms or positions themselves?
Yes, there are ways to convert recursive formulas to explicit. It can get pretty complicated pretty quick though. Yeah, well, it's well above what you would do in this class or maybe even calculus. It's pretty challenging. At least basic calculus. Yeah. All right, so now let's look at a recursive pattern and see if we can change it to explicit. If I ask you to change it, it's not going to be a really hard one to do. So there's our formula. A sub n is 5 plus a sub n minus 1. And we've got the first term. If you want to convert something to explicit, what I would do is list out the first 3. So then when you come up with a formula, you can test it on the first 3 or so terms. Okay. What's the second term going to be here?
8.
8, and the third term? 13. All right, so now the goal to make it explicit is figure out what you can do to your position number to turn it into your term. Anyone think they see a pattern that converts the position number into the term number? Yeah?
Never mind.
Yeah? Yeah?
Square it and add 4.
Square it and add 4. Okay. What's 1 squared? Yeah, 1 squared is 1, and then if you add 4, you don't get 3. That's a good guess. That's the kind of thing we're looking for. Generally, I'm not going to have you try to figure out a quadratic pattern, because that could be pretty complicated. Anyone see something else? Yeah?
Oh, multiply by 5 and subtract 2.
Yep. It's multiply by 5 and then minus 2. the hint that you should be looking for something times 5 is right there. You're repeatedly adding the number 5 every time to get to the next term. If you repeatedly add the number 5, repeatedly adding the same number is multiplication. So you should be looking for a times 5. And then you might need a plus or a minus just to adjust it based on the number you started at. Yep, the pattern is 5n minus 2. All right, so let's try this one. So this is a sequence that, again, you've probably heard of, but it's not easy to convert this to explicit. It's not even something we're going to do. Okay, if you're interested in it, you can look it up. But again, it's pretty challenging. So what I want to do is just practice working with this type of sequence. It is recursive, but it doesn't depend on just the term before the one. It depends on the term before and the one before that. So it depends on 2 terms. That means I need to start you with 2 terms. So in kind of like simple words, what is this basically saying to do? To get a particular term, you do what? Yeah?
You need to get the previous number and the one before that and then add them together.
Yeah. Any term that you're looking for is the sum of the 2 that came before it. So 1, 1 is the first 2 terms. What would be the next term in this sequence? Yeah? 2. Okay. And the next one would be? 3. 5. 8. I don't, how many did they want? The first 6. Oh, you're done. That's the first 6. So 1, 1, 2, 3, 5, 8. Right, and that's a Fibonacci sequence. It's a specific type of sequence that's in a bigger category. I think the bigger category is called a Lucas sequence. What makes it a Fibonacci sequence is you're starting with 1 and 1. If you take any 2 terms and add them together, but you don't start with 1 and 1, then it's not a Fibonacci sequence. I think it is called a Lucas sequence. Let's see. So it says that a Lucas sequence does include Fibonacci numbers. So yeah, Fibonacci numbers are an example of a Lucas sequence. There's a little bit more reading than I want to do right now. So, but I was right with that. All right. So a couple of interesting things with Fibonacci numbers. We're gonna talk a lot more about Fibonacci numbers and more about this triangle on Thursday. Does anyone know what this triangle is called? Yeah?
Pascal.
That's Pascal's triangle. And there's all kinds of patterns in it. You got 1s on the outside, and if you take any number and you add the 2 that are above it, that's how you get the next row. So 6 plus 15 is 21, 15 plus 20 is 35. There's kind of some interesting things, like if you look at prime rows, notice they start with row 0. But if you look at prime rows, every number in a prime row is a multiple of that number. So for example, let's look at row 5. Because 5 is a prime number, every number in row 5 is a multiple of 5. Is 6 a prime number? No. So every number in row 6 is not a multiple of 6. But is 7 a prime number?
Yes.
Yeah. Then every number in row 7 is a multiple of 7. So there's a lot of interesting patterns here. But the one I want to look at is this one. If you draw diagonals, okay, in the Fibonacci, in the Pascal's triangle, and you look at the hexagons where the line goes through the middle of it, and add those numbers up. Let's look at the first one. So for this first line, it goes through, don't count it if it's on the border, okay? Just if it goes through the middle of the hexagon, you get a 1. Right. Do I want to add them up or just write them down? Yeah, let's add them up. Okay. The next one, it goes through a 1 and a 1. And what do you get if you add that up? 2. Now the next one goes through a 1 and a 2. So that's a 3. The next one goes through a 1, a 3, and a 1. That's a 5. Let's do one more. 1, 4, 3. 8. What do you notice about those numbers? Yeah, it's the Fibonacci sequence. So if you add up the way we were doing, you get the Fibonacci numbers. And I could have actually slid it up one like that to get the first one. Now it goes through a 1, then a 2, and so on. Yep. So there's lots of stuff we can do with this triangle. We'll look at it a little more later in the week. Also, if you need to generate this triangle for rows that start to get really far down, we need a better way of saying, all right, 1 plus 3 is 14, 13 plus 78 is, that's going to take a while. So there are better ways to figure out these numbers rather than just adding the 2 that are above it. And we'll talk about that as well. All right, so we've talked about 2 types of sequences in terms of formulas you can write for. Explicit and recursive. Now we're going to talk about 2 types of sequences in terms of the pattern to get to the next number. So in an arithmetic sequence, that is a pattern where to get from one term to the next, you add or you subtract. That's called an arithmetic sequence. I say arithmetic. If you look it up on YouTube, some people say arithmetic, some people say arithmetic. It depends on who you talk to. But an arithmetic sequence is a sequence where you add something to the previous term, and you can add a negative, that works too, to get to the next term. The number that you're adding, or technically subtracting, is called the common difference of the sequence. Now, you might think, well, wait a minute. If you're adding to get from one term to the next, why do you call the thing that you're adding the common difference? Well, let's look at an arithmetic sequence. Okay, so there's an arithmetic sequence. How am I getting from one term to the next?
Add 2.
I'm adding 2. So where does this common difference come in? Well, take a term and subtract the one that came before it. What's 13 minus 11? There's your 2. What's 9 minus 7? 7 minus 5? 2. All right, so the common difference is basically figured out by taking a term, subtracting the one that came before it. That's what they call a common difference. And they call it common because it has to be the same for every one of them. If I gave you a pattern like this, that is not an arithmetic sequence anymore. I don't know what the formula would be for that sequence, but it's not adding 2 each time. So that is the explicit formula for any arithmetic sequence you come across. So it gives you a quick way to find an explicit formula, and you don't have to really think about it. You don't have to sit there and be like, all right, is it times 4 plus 3 times 8 minus 7. Like you don't have to do any of that. All you have to know is the first term in the sequence and the common difference. So what I want to do is go back and try that on one that I asked you about earlier. And it took people, like 15 or 20 seconds for people to look at it and figure it out. With this, it shouldn't take you any time at all. So it's the first term plus n minus 1 d. Let's go back and try it on one we already did. Okay, let's try this one. We already know what the answer should be. What's the first term in this sequence?
3.
3. And what was the common difference?
Same.
What is it? 5. Common difference is 5. So using that formula, a sub n equals the first term plus n minus 1d. Can somebody tell me what the formula would be, filling in those values? Yep.
A sub n equals 3 plus n minus 1 times 5.
All right. Now that is not what we had, but let's simplify it and see what happens. 3 plus 5n minus 5. And when you combine like terms, what do you get?
5n minus 2.
You get 5n minus 2. All right. So that formula gives you a quick way to come up with an explicit formula as long as the pattern is adding each time, or subtracting. Adding or subtracting. All right, let's do this one. Well, you're not doing that one the way it's written. Why can't you do that problem?
You aren't given a sequence.
You're not given what?
A sequence.
Yeah, you're not given a first term. You're given a recursive formula, but it doesn't give you a starting point. It doesn't give you a starting point. So let me give you the first term. All right. So we've got the first term. What's the common difference?
3.
3. So could somebody tell me the formula using the notation we just wrote down? Yeah.
5 plus n minus 1 times
3. And if you simplify that, so distribute, combine like terms, can you give me the final answer?
What did you get? 5n. No. Two. Wait, am I doing n minus 1 times 3 plus 5?
Yep.
Okay. Then you get 3n plus 2.
Yeah, 3n plus 2. Right, and you can always check it. You could list out the first few terms using the arithmetic sequence. Then you could try using your formula and make sure they match. But that is the correct answer. All right, any question? All right, let's try this one. So it says the first 2 terms in an arithmetic sequence are, find the 5th term. All right, now, realistically, we could just find the 5th term here. It's not that hard to do. But let's pretend that it said find the 5,000th term. You're definitely going to want to come up with a formula so you can do that quickly. What would be my formula for this one? So how would you write it using our
Oh.
notation?
Well, A1 would be negative A, then plus parentheses n minus 1,
Yep,
6.
yep, exactly. And then can you simplify that for me and give me a version with all the like terms put together?
Be 6n negative 14.
Yep, so
Minus 14.
6n minus 14, exactly. So now we can find the fifth term pretty quickly. Take 5, plug it in for n. And what do you get for the fifth term?
Would it be 16?
Yeah, because you're going to have 30 minus 14, which is 16. Yep. Again, I probably could have found the fifth term faster without even using this formula, but that's only because it was only 3 terms away from the last one I gave me. Any question on that? All right, let's try this one. So it says find a formula for the arithmetic sequence. Well, what do you need to know when you're finding an arithmetic sequence? What's one thing you definitely need?
Oh, you need the first.
You need the first term. We don't have that, so you need to figure out the first term.
We gotta figure out the difference between the one in position 3 and position 8, and from that difference we've got to go down to the first term.
So how do you get from 13 to 3? If it's an arithmetic sequence, yeah? Okay, so it's a difference of 10, and you're making 1, 2, 3, 4, 5 jumps. So what do you have to do each time if it's a difference of 10 over 5 jumps?
Subtract 2 each
Yeah,
time.
you're subtracting 2 each time.
So you've got to add 2 to it back.
So yes, to work backwards and figure out the first term, we have to add 2. Okay, there's our first term, 17. So now, can somebody tell me what you don't have to combine all the like terms yet, but what would the formula be for that nth term? Yeah, see?
17 times n minus 1 times negative 2.
Can you say that again?
17 times n minus 1, and 17 plus n minus 1 times negative 2.
All right. So even though you are subtracting a number each time, that's still arithmetic. You could just think of it as adding negative 2. So you're still adding something. And combine like terms, and what do we get for final answer?
They said n equals 19 minus 2n.
Yep, and I usually write it, that's fine, I would give you credit for that. I just usually put the, almost like y equals mx plus b, I kind of do it that way. So you said negative 2n, and then what was your constant?
19.
19. Yep. There we go. Any question on that? Okay. All right, so that's arithmetic. So the last sequence we're going to look at today is geometric. Geometric is not adding or subtracting a number. Anyone have a guess what the pattern is with geometric? Yep, it's multiplying. So in this type of sequence, the next term is obtained by multiplying the previous term by a constant. So here's an example of geometric. 3, 6, 12, 24. So to get a specific term, take the one that came before it and you multiply by a number. We're going to call the number you multiply by each time R. Now, last time we called what you added each time D. That stood for common difference. Anyone have a guess what the R stands for? It's along the same lines as what we did when we added a number each time. We called it the common difference. We're multiplying by a number each time, so we're going to call it
Common ratio?
Yep, it's the common ratio. And the common ratio is figured out by taking a term and dividing by the one that came before it. So if you look at my pattern, take a term, 24, divide by the one before it, 12. 24 divided by 12 is 2. 12 divided by 6 is 2. 6 divided by 3, 2. And we're going to come up with a formula to predict any term in a geometric sequence explicitly. And it depends on two things, just like the first formula I showed you. We need the first term, and you need what you're multiplying by each time. So it's a sub 1 times r to the n minus 1. This is the explicit formula for a geometric sequence. All right, so let's see if we can try this. This will be our last one. All right, so what is something that we need to know that we don't know? Yeah?
Common ratio.
Okay, so we need the common ratio. What is the common ratio in this one? Or
We would
actually,
do-
tell me how you calculate it.
So you would take the term in the term before it
Yep.
and like divide it.
And
So you would divide. So you would divide the third by the second term. So you would do 12 divided by -6, and so you would end up with -2.
Yep, so that's your common ratio. And now we need to work backwards to figure out the first term.
Positive 3.
First term here is going to be positive 3. So what's going to be my formula for the nth term in this geometric sequence? Yeah?
It would be 3 times what, -2? Oh, n minus 1.
Raised to the n minus 1. Right, let's try it on the third term and see if it works. What's 3 minus 1?
2.
2. What's -2 squared? 4. And what's 4 times 3?
12.
12. And that's exactly the term we're supposed to get. So that's how you can find a formula for a geometric sequence. All right, any questions on it? So that's pretty much everything we do with sequences. So that's 11.1. Tomorrow and Wednesday, we're going to look at a series, which is when you take all the terms in a sequence and then you add them together. And obviously, if you have a really big sequence, that could take a really long time. Well, we want to come up with a short way to add up a lot of numbers. And that's what I'll show you tomorrow. All right, let me see, I can let's just make that 1 through 13 hard. Okay, so 1 through 13 odd, 14, and then 17 to 27 odd, and 31. So we'll take a look at that tomorrow, and then we'll do 11.2, and that will be our second to last section.